Viitorul e al tău, noi punem temelia. UTCB, construim pentru România. UTCB, Universitatea de Construcții București.
Good afternoon, ladies and gentlemen. My name is Fujita of Ohsaki Research Institute. It's a great honor to have this opportunity to make a presentation about one of the SIP's research works at UTCB. The title of my presentation is Proposal on a Rational Method for Determining the Repair Order of Road Bridges. As for bridge maintenance in Japan, the local governments are obligated to conduct the inspections every 5 years for the bridges under their management. The inspected bridges are classified into 4 categories. Category 1 means sound status. Category 2 is the preventive maintenance stage. Category 3 is the early corrective action stage. And category 4 is the urgent corrective action stage. Now bridges of categories 4 and 3 are being repaired, which will take about 10 years. After that, preventive repairs are going to be carried out to the bridges of category 2. However, there is a problem in the preventive repair for category 2 bridges. Since there are no significant differences in the deterioration states among the category 2 bridges, it is not appropriate to determine the repair order only based on their deterioration states. We need to assess the performance of the deteriorated bridge elements. In order to solve this problem, we propose the following. The performance of the deteriorated bridge elements should be assessed quantitatively, considering loading and environmental conditions. Then the repair order of the targeted bridge is determined by the reliability indices for the performance of the critical bridge elements. The target of our research is the deterioration of RC elements of road bridges. The objective of the research is to propose a rational method for determining the repair order of category 2 bridges by considering the environmental conditions such as the chloride ion concentration, seismic effects, traffic flows, and importance. The repair order of the bridges is determined based on the reliability index for the performance of the critical RC element. The developed results are to be applied to the road bridges with a span of 15 meters or more in Tottori Prefecture. 2 limit states of RC elements shown in the figures are verified. One is the bending capacity of the deck slab subjected to vehicle load. The other is the bending capacity at the bottom of the pier subjected to the bending moment caused by seismic load. The performance of the critical RC elements are assessed for each targeted bridge by this inequality. R sub D is the bending capacity and S sub D is the bending moment in this case. Since there are significant variations in both bending capacity and bending moment, coefficients of variation of 15% and 20% are assumed respectively. These figures show the deterioration mechanism of reinforced concrete due to chloride ion. At the incubation period, the chloride ion invades into the concrete and corrodes the rebar. Then the corroded rebar expands and pushes the surrounding concrete which causes the crack at the river. This is the development period. At the acceleration period, the crack propagates to the surface of the concrete. And at the deterioration period, the cover concrete spalls. As the deterioration progresses, the river corrodes increasingly, and the river mass decreases accordingly. Consequently, the bending capacity of the RC element decreases. The river mass loss rate is calculated based on the corrosion-induced crack width with this equation. And the river corrosion rate is calculated based on the chloride ion content at the river position by this equation. The chloride ion content increases as time goes by. These equations are to be replaced by the result of SIP's research. The bending capacity of the RC element with the corroded river is calculated over time. In the case of earthquake, the seismic hazard analysis is carried out to obtain the maximum ground surface acceleration at each bridge location. For example, the maximum ground surface acceleration of 356 GAL is obtained for the 10% exceedance probability in 50 years. When the earthquake occurs, the inertia of the girder acts on the top of the pier and causes the section forces at the bottom of the pier. The performance function and the assessment inequality are shown like this. R is the resistance of the RC element, and S is the response caused by loading. In case of normal distribution, the probability distribution of R and S can be described like this. Then the reliability index is simply calculated by this equation. Reliability index beta corresponds to the occurrence probability PF of the limit state. This figure shows the reliability index change over time. The vertical axis is the reliability index beta, the horizontal axis is time. It is defined that the repair timing is a time when the reliability index reaches the management level. The management level is calculated depending on the management class. The targeted bridges are classified into the management classes A, B, C, and D, as Dr. Wakahara mentioned. The management classes are decided based on the assessment by public asset simulator. PASS is a system based on geospatial database that integrates various administrative data such as population, housing, traffic, facilities, and disaster information into a road network model. Class D bridges require consideration for potential decommissioning due to reasons such as low traffic volume or the availability of alternative routes. So the Class D bridges are treated differently from Class A, B, C bridges. Our proposed method here is applied to Class A, B, C bridges. Then the management levels are calculated by this equation. The management classes are distinguished by the social criterion factor S. The repair timing is calculated for each bridge. Then the targeted bridges are sorted in the order of the repair timing, as shown in this table. And the targeted bridges are repaired in the order of this table. This is the rational repair strategy we propose. I'm now showing a numerical example. I set a bridge model whose structural dimensions and lever arrangement are shown in these figures. And the input data for the calculation are shown here. That is, coordinates of the bridge location, bridge length, traffic volume, concrete compressive strength, lever yield strength, water cement ratio of concrete, corrosion-induced crack width, chloride ion content at the lever position, and the residual service life. The measured values such as crack width and chloride ion content are included. This example is an earthquake case. By the seismic hazard analysis, the horizontal ground surface acceleration of 356 GAR is obtained. I converted this acceleration to the horizontal seismic coefficient of 0.231. By the structural analysis, the bending moment and the actual force at the bottom of the pier are obtained, like this. You can see in this table, chloride ion content, lever corrosion rate, lever mass loss rate increase as time goes by. On the contrary, the bending capacity decreases accordingly. Then the reliability indices are calculated as shown in this table. The calculated reliability indices are plotted in this figure. The vertical axis is the reliability index and the horizontal axis is the elapsed year. The management level is calculated depending on the management class. For the management class A, the management level is 1.92. For class B, the management level is 1.82, and for class C, the management level is 1.74. Then the repair timings are obtained as 7 years for class A, 37 years for class B, and 52 years for class C, respectively. In order to estimate the repair cost, necessary unit prices for repair method and temporary works should be prepared. This table shows an example of unit prices. Then the approximate repair cost can be estimated in advance for each bridge. The targeted bridges are sorted in the order of the repair timing. This is the repair timing. The bridges whose estimated cost fit the annual budget are to be repaired in the order of the repair timing. This table shows the case that the annual budget is 5 million euro up to the bridge whose accumulated repair costs reach the annual budget are to be repaired. This is one of the rational repair strategies for Category 2 bridges and helpful for the bridge maintenance of the local governments. I'd like to conclude my presentation. First of all, it should be noted that the values of the reliability indices vary depending on the calculation models and the parameters. Therefore, the absolute values of the reliability indices cannot be directly used for assessment criteria. However, the relative comparison of reliability indices calculated under the same calculation models and parameters can serve the varied assessment criteria. Consequently, to determine the breach repair order based on the relative comparison of reliability indices is considered as a rational approach. In the future, the following items are going to be updated through SIP's research works. River corrosion rate model is established based on the corrosion experiments of RC specimens. Method to calculate the management level is investigated. Measurement method of chloride ion is improved for the practical use. Measurement method to obtain the crack properties from photos by using AI is established. Practical method to estimate the approximate repair cost is investigated. The proposed method will be adjusted or modified by the result of the inspections every 5 years. Thank you very much for your attention.
UTCB, viitorul e al tău, noi punem temelia. UTCB.